Welcome to the Nautel webinar focused on HD radio FM digital solutions to the increased injection levels of HD carriers. I'm Chuck Kelly. We have a great group of folks here to help us explore this topic, including Mr. Mike Woods, who's sitting next to me here in Halifax, Nova Scotia. Mike is Nautel's Head of Development. Hello, Mike.
Good afternoon.
And we have Mr. Hal Neller, many of you may know, Market Development Manager for Nautel, calling from his office in Punta Gorda, Florida. Hey, Hal.
Good afternoon, everyone.
Glad you could join us. I guess it's a little warmer down there than it is here in Nova Scotia.
I may break down and turn on the air conditioner.
So we want to talk about a number of things today related to the discussions having to do with increasing digital HD injection ratios, and why that's necessary, what different strategies there are to get to those increased injection ratios, the alternatives you have in coverage, transmitter considerations, things we as a transmitter manufacturer do to make sure that these transmitters can be can handle these additional power levels, various different solutions. And we're going to get to your questions as well. You may notice that in the GoToWebinar application that you've got open on your screen, there's an opportunity there for you to type questions. And please do that. And near the end of the webinar, we'll get to that. Understand that there may be some questions that we may not be able to answer today. We actually have a webinar specifically on the subject of HD Power Boost, which will be early next year, and we're going to have Mr. Philip Schmidt here for that, and he, of course, is the guru of that technology, and he'll be able to answer specific questions in that regard. So we'll try to keep this rapid. We'll try to make it non-technical to begin with so everybody can get on board, and then we'll get as technical as we need to as we go forward. So I would be remiss if I didn't mention that this is the 40th anniversary of Nautel. Nautel actually started in 1969. The first solid-state broadcast transmitters were introduced in 1972. And the photograph on the right-hand side is some of the employee population here in Nova Scotia, but we also, of course, have offices in Bangor, Maine, and factories. In Bangor, Maine, we also have another facility down in Quincy, Illinois, for customer service. So the entire organization now is 40 years old, and we're very proud of that. And from the very beginning, Nautel has been a company which has been led by engineering. It is an engineering-led organization. There are 37 design engineers here, and there's no question that engineering leadership is what causes us to take on things that have never been done before. I mean, the solid-state AM transmitters that we introduced nearly 40 years ago, nobody thought you could do solid-state AM transmitters. That's what tubes were for. And nevertheless, every step of the way, Nautel has been a leader in bringing solid-state technology to the marketplace, as we are today. So the question for today is the digital coverage challenge. The goal is to assure that your digital coverage has equality with your analog coverage. So we want to have the digital and the analog have the same coverage area. But there's a problem there, isn't there? Because analog signals degrade linearly as you drive away from the transmitter site, and digital signals have what's called the cliff effect. So my first question is going to be for Mr. Hal Neller, because he's got a lot of experience in this area. Hal, how do people rationalize the gray zone of trying to compare analog coverage to digital coverage?
Yeah, it's difficult and somewhat subjective, Chuck. If you look at that little graphic that's on the page there, that line, kind of a circle, is the 54 dBu contour of WKLB in Boston. And you can see some red areas inside that line. That's where the digital has fallen out. And, of course, quite a bit of red right outside that. But if a person is driving down that highway out of Boston, southeast towards Cape Cod, know when they pass that magic contour line, their radio is going to continue to play for, possibly quite a while. And so the idea is that now we really the radio stations want to look at it in terms of real-world reception. if the people can hear the analog signal and they can't hear the digital signal, that's a problem. So hence we have come to this power increase situation.
Okay. And the bookends to this particular conundrum, if you will, on one side is, as you say, providing equivalent coverage for analog and digital. And on the other side is we want to avoid any kind of interference, not only to adjacent channel signals, but also to your own analog. Right, Al?
That's absolutely right. And as you increase the digital signal beyond a certain point, and it's somewhat receiver dependent, you can create white noise within the HD radio receiver on your own station, even without the potential, in some cases, of creating interference to an adjacent station.
Yep, and if everything is going perfectly, though, that number is beyond the -10 injection level, right?
Yes, absolutely. Ubiquity's tested a lot of receivers and as NPR labs, and they said the worst of the receivers typically start to have noticeable noise at about -6.
Okay, so we'll get to other issues that come in place here, but that it kind of brackets what we're trying to attack today. And of course, every broadcaster has got to become cost effective and got to remain cost effective. So whereas it might be very tempting to sit here and talk about buying whole new transmitters and replacing everything, we have to stay cost competitive. So one of the goals of today is going to be to look at all the options, but to try to avoid simply replacing your transmitter. So we're going to go forward with this. One of the things that's driving all of this is noise floor. I did a paper earlier this year on the subject of noise floor, and it seems to have hit a resonant chord in some folks because a lot of people anecdotally know that their stations don't get out as far as they used to. They used to be able to listen in this spot or that spot, and it isn't that their transmitter isn't putting out as much power or their antenna isn't as efficient. It's simply because the noise floor is rising around us, and it's because of so many new products coming out. You know, a microprocessor is a transmitter at 100 megahertz, and we have a lot of noise sources. Hal, you ran into one of all places in Alaska, didn't you?
Yes, one of the engineers up there noted that he was in a fairly marginal reception area for some of the HD radio signals, and he had an HD receiver in his bedroom and a compact fluorescent in his bathroom, and when he would turn on the light switch in the bathroom, the HD signal would go away. And when he'd turn it back off again a few seconds later, it would come back. So I think in a slide that you're going to have coming up real soon, you're going to actually see exactly why that happened.
Yeah, and let's get to that slide. You know, basically, this is the HD radio signal. In the center here is the analog FM signal, and on the sidebands are the traditional -20 sets of HD radio sidebands. So these are down 20 dB from the carrier of the analog FM, and again, there are sets of orthogonal frequency division multiplex OFDM sidebands. And as that noise floor comes up, it begins to approach the level of those sidebands. Now, what we see here graphically is roughly a 4 dB increase in level above the noise floor for the HD sidebands, and that's pretty important, isn't it, Hal?
It is, and likely this is the scenario that Chuck Licatus had in Alaska, where he was barely able to receive his HD radio signal until he turned that light on.
Okay, so 4 dB is approximately the point where receivers can no longer dig out those sidebands.
Right.
Okay. Now, if it goes beyond that, then you're in a situation where you can no longer hear HD at all. And one of the things that's interesting here to understand is that while the main channel of HD the receiver will automatically blend over to analog, if you're listening to a subchannel, if you're listening to one of the multicasting channels, you're blending to analog, which is a whole different program, and so you really do have the cliff effect that we've talked about. Now,
absolutely, and you know the other thing is that you know some people have said, well, the receivers need to be more sensitive. The problem is when you have a noise situation like this, a hotter front end on a receiver is not going to generate a better response for the listener. He's going to be buried with the noise, regardless of how sensitive that radio is.
Yep, that's right. So what's happening is that we're not limited by the receiver sensitivity. We're actually limited by the site signal-to-noise ratio. There's an interesting corollary here, gentlemen, and I'm reminded of a friend of mine who was the first guy that put on HD radio in Eastern Europe. His name is Andrei Karpy, and he lives in Kiev, Ukraine. And the guy is a PhD electrical engineer, and he happens to own 100 radio stations. And this guy put on HD radio in Kiev on his own radio station. He used separate antenna installations, which gave him a complete control over the injection ratio, and of course he had none of the legal impediments to making changes that we might have in North America. So what Andre did is he drove around the city of Kiev and said, you know what, in this noisy environment I'm in here, I don't think I have equivalent coverage on my analog and my digital, so I'm going to turn up my digital. And he did. And he turned it up, and he found that the sweet spot was right about minus 13.
This is like 6 years
This
ago.
is a long time ago, Mike.
Yeah.
And he had independently arrived at something that we in North America didn't really understand and flesh out for a couple of years after him. And he found out that if I went much above that minus 13, he had the potential of hearing the digital noise in his analog carrier. So it's kind of interesting to think back about what this guy faced and figured out a long time ago. And the question he was trying to answer, as we all do, is how much injection is enough? So what we have to do in those scenarios is analyze our digital coverage. Are we in a high noise environment? More accurately, is the point at which our analog signal is starting to fade in a high noise location? And if it is, it's likely you're going to need more of the digital injection levels. Another thing you have to analyze, interference to other stations. Think about, as we've discussed, interference to your own analog. And then we have to talk about, right now we are not yet at the point when minus 14 is authorized. We have, Hal, fill me in, but I believe the situation is that there's kind of a consensus within the industry that minus 14 is something we aim for, but there's also a desire to get, in some cases, beyond that, to minus 10.
That's correct. A group of industry people from commercial broadcasting and public radio met with the FCC about 2 weeks ago and presented this compromise that was all signed off by everyone. The FCC has indicated that they will provide some answers to this fairly soon. We don't know exactly what soon is, but we're presuming in the next few months. And that everyone has come together. But the 14 dB is the compromise point. It gives a significant improvement, but doesn't necessarily help everybody all the way. So some customers will decide that they need to go all the way to minus 10. And those areas are what we still have some industry work to do. For example, one of the things is if a station has a sideband problem, close adjacency on one side, we could hold their carrier levels at minus 14 on that side, but if their other side is clear, we could, by using asymmetric power, we could raise their signal of the HD carriers on the good side or the clean side up to minus 10 and affect a significant improvement over, say, what the overall minus 20 situation would be. So yes, there's still some work to do, and the ultimate goal for some stations will be to get to minus 10.
Great point, Hal. The asymmetrical sideband power is something that is being discussed a lot. I want to bring Mike in and ask him, Mike, how hard is that to do from a transmitter manufacturer standpoint?
Well, just to turn it on and do it, the capability is there right now. To do it well, to take advantage of possible peak reductions takes a little bit more time. Mm-hmm. So we want to do it well.
Yeah. But today you could sit there if you wanted to
you could sit
and
there,
set up the different ratios.
Yeah, the abilities are there within the current software.
But if we want to maximize, the HD power boost type of algorithms,
exactly,
then we have to do a bit more work.
But we are certainly looking into it, that's for sure.
Okay. Now let's talk about the various strategies that stations can use to raise the injection level if they so choose. One is the possibility of antenna upgrades, and we're going to go into a little bit more detail on that. Digital-only boosters. I've heard that mentioned a number of times, and I think it's important that we discuss it for a second because I think perhaps people will think about this concept of digital-only boosters, and misunderstand that it could solve some problems. It can also create some problems, because as you would drive towards a digital-only booster, the ratio of the digital to the analog signal would increase, and you're going to be driving into a situation where you will eventually have interference as you drive through that transmitter. So one of the advantages of the HD radio system as a total system is that wherever you go, the analog-digital ratio stays pretty much the same. But if you start getting into digital-only boosters, that's kind of out the window. So that's a little bit off the table, in my opinion. Let's go forward. Transmitter solutions. There is the possibility of adding separate digital transmitters, high power combined, space combined. We're going to talk about those. We're going to talk about higher power hybrid mode transmitters, where the transmitter is making both the analog and the digital signal at the same time in the same transmitter. And we're also going to talk about HD Power Boost, which is Nautel's patent applied for technology, which is a suite of tools that allows us to coax more power out of a transmitter for injection level than you would be able to get without this mathematical magic. So we'll go look more at those things. Now, on the antenna options side, the idea here is, what if you have an antenna on the tower that's, say, a 2, 3, or 4 bay, and your transmitter is maxed out at -20. One potential strategy that you've got is to either replace that antenna or modify that antenna to have more gain. Thus, you can back down your TPO and get more HD injection level out of that, keep your ERP the same. This is a strategy that is actually quite efficient in terms of maximizing the transmitted power in the sidebands and keeping your ERP approximately the same. It's high efficiency. It increases injection without changing the transmitter. On the other hand, you're going to have to take a look at issues like how much space you got on the tower, wind and weight loading, and the fact that if you try to do an in-place upgrade on this, on the number of bays, there's a lot of issues with impedance matching. It's not quite as simple as simply tacking on a couple other bays with Elmer's glue. Your antenna manufacturer is going to be your friend when you analyze this option. Another possibility is high power combined. I know there's a lot of stations that went on the air very early in the HD radio process with high power combined. When we change from a -20 injection level to a higher injection level, all the assumptions that are made in the design of a high power combined site change. And Mike, you've done a lot of analysis of this, and maybe you can comment about what's going on.
Yeah, if you look at system efficiency, which is usually one of the most important, parameters.
Overall efficiency, AC in to RF out.
Correct. If you look at that and you optimize the coupler ratio, you'll find that at -20 dB injection, the optimum coupler is around 10 dB, and that's what we've all kind of heard about.
This is this device right here.
Right. So that's allowing the analog,
also known as a 10 dB hybrid or an injector.
Right. So that's providing isolation between the two transmitters, and it's allowing part of the analog signal and part of the digital signal to make it to the antenna, and of course some of it goes to the reject load. So,
in fact, 11% of the analog and about 90% of the digital at the -20 injection.
Hence the 10 dB.
Exactly,
so
goes into the reject.
10-to-1 ratio. So
that's right.
As you go up in injection level, so as you approach 10 dB, the optimum coupler actually works out to about 5 dB, which is a significant, and remember, this is for system efficiency, so you're now throwing away more of your analog.
About 25% of your analog.
25% of your analog, and that's so that the digital transmitter is a kind of a reasonable size.
Right.
If you had stayed back at the 10 dB coupler, you would have needed 10 times the digital power on your digital transmitter.
Yeah.
Which is, obviously a very large change.
So the efficiency of a high-power combined system degrades significantly as we go to higher injection ratios.
Remember, these are non-synchronous signals, so,
right.
So there's no cancellation at the reject port as in the case with a kind of a normal, 3 dB coupler. So you need to throw away power in this configuration.
It's expected.
It's expected, and the higher the injection level, unfortunately, the more power you're going to throw away, and hence efficiency drops.
Okay. All right. So people who have a high power combined situation
Not
today
as attractive at -10.
going to have to take a look at different options.
That's right.
Yep. Okay. Let's talk about space combining, also known as dual feed antennas, also known as, putting two antennas on the tower. It's the most efficient way of doing HD radio.
That's
There's no
correct.
power being thrown away anywhere.
No coupler, no reject load. You're both transmitters directly coupled to antennas. So it's elegant in that way, but increasing the digital path, obviously you have to make sure that digital antenna can handle the increased power. And
That's a big point, because you're talking about 10 times more
right.
power.
I mean, did you architect that system to handle 10 times? Probably not. So your line size and your the power capability of the radiators, all of that needs to be
And when you talk about a digital-only signal going into an antenna, you have to consider not just the RMS power of that signal, but the voltage peaks too.
That's right. It's got about a 6 dB peak to average ratio, and so in a voltage scheme that would be twice voltage or 4 times power. So you need to consider those peaks.
Now there's another issue that comes into this as well, and it's a little bit difficult to understand, but I'll do my best to explain it. And that is, when you have a separate antenna, if you have two antennas on a tower, one above the other one or whatever, the vertical patterns of those antennas, they should have the same number of bays, they should have the same mounting arrangement.
Ideally,
so we want to make them as much the same as possible. But being higher than the other, one over the other, means that the nulls, as they appear on the ground, may happen at different places, which may mean that there are times when the analog signal goes into a null and the digital signal hasn't, which then unbalances that precarious relationship between analog and digital, and it may mean, in fact, that you get interference in your analog from your digital. Hal, you had some experience with that?
Yes, about 3 years ago, Mike Hendrickson from Minnesota Public Radio did a paper at NAB about this subject. They had a 1,000-foot tower in a highly populated area of Minneapolis-St. Paul, and they were using two separate antennas, a 10-bay for the main analog antenna, and then their aux antenna, which became the HD antenna, was like a 3-bay antenna mounted a little lower on the tower. And in this populous area, they had problems in both homes and in the heavy traffic on the street driving by. So you could actually happen to stop for the traffic light and wind up in exactly the wrong spot, and the station would totally washed out with white noise if you were listening in analog, because you hit a null from that analog antenna, but you were not in a consequential null for the digital antenna, and the ratio went completely wrong. The analog was gone. And so they talked about how to watch out for this kind of a problem. So if you're in a highly populous area with your transmitter site, you need to watch that. If you're 15 or 20 miles out of town, that isn't as critical an issue.
Right, and certainly the height of the tower makes that tougher.
Yes, the higher it is above the populous area, the worse the situation becomes.
So this isn't too much of an issue if we're talking about antennas which are either dual feed or staggered within the same aperture of the antenna, because the antenna's center of radiation is the same. But then if that's the situation, you've got to be very careful about the coupling between the digital and the analog so that we don't create RF intermodulational distortion in those two transmitters.
That's correct. And also, you should use the same number of bays, because if I had, say, a 12-bay digital or analog antenna and I put a 4-bay digital up, I could still have differences in my nulls.
Absolutely. So with regard to these RF IMD, if you've got a design which was done for a -20 installation and you go to -14 or -10 or something, you need to reanalyze and see whether or not additional filtering or circulators may be necessary, and that's a big issue. Now, another point that's important to make here is that Nautel is constantly doing new development and work on maximizing the power output of the transmitters, and Mike's team spends a lot of time in this. And one of the things, just recently, we've been making some pretty substantial improvements in the performance of our NV series transmitters in all digital modes, so as would be used in a space combined installation, or for that matter, a high-level combined installation. And we have gotten as much as 11 kilowatts of all digital power from an NV20. That's quite an accomplishment, Mike.
Yeah, that's a significant improvement over our current published numbers.
Most people, less than 5 kilowatts or something like that is what you'd expect out of a 20 kilowatt transmitter.
Yeah, 5 to 6 kilowatts.
Yep.
So we're a significant, amount above that.
Okay. Now let's talk about higher power hybrid transmitters. The big advantage of this is that it's simple architecture. It's a single box installation. There are some significant negatives, though, and then those include higher HD injection level, which may reduce the analog TPO capability, may need to replace your transmitter or combine with another for higher power, total power. And, of course, when you go to a higher injection level of digital power, your transmitter is going to reduce efficiency. So, on the other hand, the good news is that Nautel has developed some technology called HD Power Boost, which is a suite of tools that mathematically adjust both the digital and the analog signal and how it's created in the transmitter to maximize the output power of HD and the capability of the transmitter. And it's a suite of tools. Mr. Philip Schmidt has done a lot of work on this, and he's presented a number of papers at the NAB on this subject, and it really does work. It makes some huge differences. As a matter of fact, we'll get to more of that. What I do want to talk about now, though, is what do we as manufacturers, Mike, do in order to prove what the capabilities? How do you go about maximizing the power of the transmitter, and how do you measure it to make sure? I'm sure there's people out there that believe we just turn the power up until smoke comes out and then back it off a little bit.
Right. Well, that's not the case, thank goodness. Two of the main limitations of the transmitter, there are many, but two of the main ones are you need to be able to have a RF emissions that meets the RF spectral mask that's been adopted by the NRSC.
Under the specific conditions that NRSC has set up.
That's right.
Certain modulation conditions, et cetera.
It's 1 kilohertz, 100% modulation on the analog carrier for a hybrid signal, and 1 kilohertz resolution bandwidth, then averaging. So that spectral mask, very, very important. And transmitter linearity affects that. And if you go into limiting, if you're clipping your peaks, you will cause intermodulation distortion, which will start to invade that space of the spectrum. So that's one of the main considerations. Then of course the other one is the RF amplifiers. Their current and voltage need to be maintained within design parameters, and especially the temperature rise of the junction of the semiconductor junction.
Let's remember that when we put a transmitter into HD mode as opposed to analog mode, we're shifting from Class C to Class AB.
That's correct.
And inherently, a Class AB is not as efficient as a Class C amplifier.
And not only is it's not just Class AB, it's Class AB with a reduced RMS output, because remember this
because the peak to average ratio.
Right, the signal now has a peak to average, so it's less efficient. If it was Class AB running at full power,
okay,
it wouldn't be quite so bad. But so efficiency has gone down. So we need to map the temperature rise of the silicon inside this device to make sure that it doesn't come close to the 200 degrees, which has been set by the manufacturer of the device. And we have our own design rules that
we have a safety margin built in,
correct,
both in terms of our adherence to the spectral mask, as well as in terms of having headroom between the maximum temperature of the device and what we are doing.
That is correct.
And that's how we establish the reliability of the transmitter. So what are we looking at here, Mike?
So these are some of the tools that we use in measuring.
What's this device here?
That's a thermal imager. So that's an infrared device that will you need to set up, obviously, the focus and the emissivity, which is how much reflection there will be of the IR energy.
So that's a camera.
Effectively, yes.
And you point the camera at the transmitter.
At the device under test with the temperature eyes involved.
And you get a photograph like that.
A picture like that. So.
And what are we looking at?
It's not immediately obvious, but that is the FM FET, field effect transistor, that's used inside the RF amplifier.
Okay.
And it is a Gemini device, so it's Gemini being twin. It's got two sides, a left and right side, which is in a push-pull configuration.
So that's the left side, and that's the right side, and these are the drains of the FET.
And that's the where all the power is being dissipated. So obviously it's the hottest, red, and then white indicating the hot areas.
And then this area here is actually the package that we're talking about. And golly gee, I can even see a Phillips head screw
That's
right there.
Right. Yeah, you can see the Phillips head screw, and it's obviously not at the same temperature as the.
It's a little cooler.
As the semiconductor, yes.
And then if we convert to natural light, it looks like this.
Right. So we take our FET, and in order to get a good picture, we need to be able to look exactly, directly onto the semiconductor. So we have to take the cover off the FET. And
how do you do that?
We put it in an oven at about 140 degrees for about 20 minutes, and eventually breaks down the epoxy holding on the ceramic cover, and we can pop that off. And then we have to apply a coating to this so that the camera and the emissivity is properly calibrated. And so that you can see some overspray there, but it's a silicone compound that we spray on that, and it's a dielectric. It doesn't cause any electrical changes.
Okay.
So when you're looking at that, you can then pick out the hot spots. On the previous picture, it was around 180 degrees.
Mm-hmm. So we had about 20 dB or 20 degrees headroom.
That's right, Celsius headroom on the manufacturer.
Excellent. Okay. So now let's talk about the entire transmitter range for the NV. The NV goes from the NV 3.5 all the way up to the NV 40, and then we can offer dual versions of all of these. We've already offered some, and it ships some. So in effect, we can go from less than 3.5 kilowatts to 88 kilowatts of analog power, or up to 60 kilowatts at minus 14 dB, or up to 42 kilowatts or so at minus 10.
Right.
This is something which is unprecedented in solid-state transmitters and pretty darn hard to do even with tube-type transmitters. So the NV series has really changed the way that people look at HD radio, and the things that we're now able to do with the NV series we'll show in a second. The specific innovations of the NV include high power with no tuning and no tubes, more redundancy and less downtime. There's no single point failure, or very few single point failures. It's not like a single tube where a tube could fail and you're suddenly off the air. There's advanced instrumentation and control, which we'll show in a moment. One really important point is that there's a substantial difference, Mike, between the turnaround loss in the output of a solid-state transmitter and the turnaround loss in a single-tube transmitter.
That's right. And this characteristic is important, especially for dual or antenna-fed systems, or any chance where you have, one signal feeding back into the transmitter from an interfering source. So the turnaround loss of solid-state is of the NV is guaranteed at 20 dB or better.
And a typical tube is like, what, 6 or 7 dB?
6,
yeah,
7,
something like that.
On the Q of the
That's a huge difference, and it may, in some situations, keep you from having to buy a circulator or additional filtering or something like that. The NV series is also a bit unique in the fact that you can really, from remote control, you can actually adjust this thing from all analog to all digital and all points in between.
That's correct. You can adjust it for any hybrid injection level or any digital operating mode, any power level, yes.
And it will
very flexible.
And we can set it up to optimize itself at those individual points, because there's a lot of things that change.
Yeah, that's right. The pre-correction curve, which are the coefficients we apply to the forward path, they would change depending on the injection level and the mode. And the voltage that we put on the amplifier itself, we like to optimize that to get the best efficiency we can.
And we do that by keeping tables of things stored in the transmitter, so you can return to it and change very quickly.
You can store the lookup table, yes, that's right, so you can return to that very quickly.
Okay. And we also talk about the fact that it's very small. I've had people walk up to an NV40 at a trade show and walk around the back looking for the rest of it.
Yeah, I mean, it was certainly revolutionary. It probably reduced the cubic inches per watt by about 50% compared to what was on the market before that.
Okay, I want to take and turn on an NV series that we actually have in the lab as we speak, operating, and let everybody see that. Hopefully you're all seeing the NV series now. Make very sure. Yep. So we're seeing here the AUI, the Advanced User Interface of an NV series. This is what is on the front panel of the transmitter, and if the transmitter includes a web or a web server, so that wherever you are, you can have your browser open and you can log into it and see this exact same screen. And you can see that we've got our test equipment set up here. There's a spectrum analyzer. This is showing the lookup table, which is correcting for some of the nonlinearity of the transmitter. Over here we've got a constellation view showing the HD radio QPSK carriers. And we have a Lissajous plot, which is at this point in time doing digital, so it isn't telling us as much, but it does provide a lot of information. So first off, let's take a look at this spectrum analyzer. Mike, this is a real instrumentation quality spectrum analyzer, isn't it?
It is, and we've compared this to Agilent, Rodensport's, other lab level analyzers, and been very happy with its performance.
So what we're
you can use this certainly to verify your intermodulation distortion products within your channel.
We are actually looking at 100 dB of dynamic range vertically, and we are looking at 1 megahertz frequency spectrum left to right here.
Right. So this is an NV20.
Yep.
And we've got it set up right now to run at 16,000 watts. And you can see on the top banner, that's the analog power.
And above that, we're seeing that this injection level, we're actually operating this right now at minus 14 dB.
That's correct. And
even though this is a 20 kilowatt transfer, we're getting 16 kilowatts out of it. That's
right.
Pretty good.
That's pretty impressive. Yep.
Okay.
And you can see the mask. And,
we're meeting the mask, with probably more than 3 dB of room underneath the mask.
And then the other thing is the analog carrier is being modulated 100% with a 1 kilohertz tone.
Which is according to the NRSC standard.
Correct.
And the specifications of this spectrum analyzer are in accordance with regard to the resolution bandwidth and the averaging with the NRSC standard.
That's correct.
So we're all comparing apples with apples.
Exactly.
Okay. Another thing that I think is pretty cool is we can actually go into this same signal here, and let's change what we're looking at. Let's change and make it an audio spectrum analyzer. Now we're looking at the composite baseband.
Right. So up to 100 kilohertz on the baseband path, and you can see we're operating in mono, so there's no 19.
Or 38 kilohertz double suppressed.
Yeah. So there's only one tone there if you put the marker on it.
Yeah, let me see if I can do. There we go. How about that?
It's 1 kilohertz.
Down 6 dB from maximum.
Right.
Right. Okay. All right. And let's go back. One of the things that's interesting is we also have the capability of not only looking at the RF signal as it's seen at the output of the transmitter, but we also have the opportunity to look at it directly in essence, the DSP of the exciter, the FPGA.
Yeah.
And so you can see really a perfect HD radio signal.
Right. So that is what's being used to compare to the reverse path signal in order to create the coefficients for correction.
Mathematically ideal.
Correct.
Okay. But that's not what we're actually...
Very few nonlinearities in the digital domain.
It doesn't look like there's hardly any, as a matter of fact. But there we go. That's where we're back, and you'll see it average down, and again, we'll get to our 3 dB. So that's how the spectrum analyzer works. Now, what I want to do is I want to go ahead and change the injection level. So I'm going to go up and hit this, and it's going to take me into presets. I'm going to load a preset here.
And earlier I created presets for -10, -20, and -14.
Right now we're at -14. Let's just go to -10. What do you say?
Load up that preset.
Save and activate. And you'll see here that the power goes down to 0 and then starts building up right away.
Right, and also in this preset, you'll see -10. If you click that, Chuck, you'll get a drop-down or a pad.
I can type in anything I want.
You can type in anything you want there. There is a little bit of optimization that we like to do. The PA voltage, and saving the lookup table.
But if all my analysis says I want minus 11.4 dB,
No problem.
type it in.
Type it in where you go. And,
Okay.
And so, but those presets that I've done have optimized, for efficiency PA. So that's why we've saved them.
Okay, so we're getting 11.5 kilowatts out of this transmitter right now, again meeting the mask, and a 20 kilowatt transmitter at minus 10 injection level.
That's right.
That's pretty cool.
And I guess it's important to say that this is running without HD Power Boost.
Right. This is just native. HD Power Boost is an advantage beyond this.
That's correct.
Right. Okay. Now let's talk about these meters on the right-hand side here.
User configurable.
Yep.
When we were at minus 20, HD power was 1% of total power.
Mm-hmm.
And where it's only 1%, most people didn't consider it, relevant enough to separate it out into a separate analog and digital power meter measurement. So when you set the power level of the transmitter, you were setting it to your analog TPO, but theoretically you were 1% below.
You're never going to see it on a bird watching.
No, exactly. Now at minus 10, being, the digital power is now at 10% of the power, it's a significant portion, and we need to be able to look at that as separate components. So
Right.
the top banner shows
Here.
power analog, and that's
Yep.
that's a kind of a default. It will always go to analog when you're in the hybrid mode of the transmitter.
Sure.
And under the meter section on the right, user configurable, we've allowed you to call up analog power, digital power, so that's the sideband. So
Right.
look at that. If you do the math, 10%.
How about that, huh?
And then total RMS would be those two added together.
Pretty simple. Now these are pretty cool. DC to RF efficiency.
Right. So during our evaluation of the transmitter's capability in HD mode, we found certain metering parameters to be very useful. So we've included them on the latest software version of the transmitter. DC to RF efficiency has actually been there for a few releases now, but the one below it, average PA dissipation. We've determined that the power in the semiconductor device shouldn't go above about 160 watts for 30-year reliability
Right.
on the MTBF curve.
Right.
And you can see right there, so we're up at 150.
What it's telling you is we're pushing this transmitter pretty hard.
It's close to the top of its capabilities, but still within
And
our
here's-
design rules.
And here's our headroom that is part of the Nautel reliability issue.
Exactly.
Yep. Okay.
Yep.
Good. Good. So you can see that there's a broad spectrum of things that we can analyze from the AUI, and you don't even have to be in front of the transmitter. You can be at home or in your corporate headquarters and manage and monitor, or even change the HD injection level of your transmitter remotely. So that's what the AUI does, and I hope that that's useful information. Let me switch over. I want to show you. We'll go back to this PowerPoint here, and there we go. Now, let's talk about HD Power Boost. We've mentioned that Philip Schmidt had some really good ideas in the shower one day, and he's been doing presentations on it, and it's actually coming to fruition. These algorithms, these mathematical algorithms that require incredible processing power.
Yes.
They provide, the bottom line for our customers is it provides more power out of the same plate value or transmitter size of a transmitter, at the same time offering higher hybrid mode efficiency.
That is correct.
Pretty cool. You can have your cake and eat it too.
Right.
And this is implemented as an upgraded software suite in a very high power FPGA in the next release of the NVE
Right.
Exciter.
So the next hardware release of the Exciter will have an upgraded FPGA capability, and FM Power Boost, HD Power Boost rather, will be able to run locally on that hardware without any external computers. Or, I mean, if you've seen our demos at previous
NAB, yeah, sure.
there was some significant hardware to get it to
Oh yeah,
run.
was it 4 processors or something in parallel or something?
But that's all been eliminated now, and it's all running on the hardware inside the transmitter. So
there's an upgrade path not only for people buying new transmitters, NVE series or NV series, but also for people who had NV transmitters purchased before.
That's correct.
And potentially, as time goes by, we'll be able to upgrade V series transmitters in the same
I
fashion.
could see this technology migrating to a standalone hardware solution as well.
Let me put you on the spot. Could I update brand something else?
Certainly possible.
Okay.
The algorithm works on an HD signal.
Okay. So for those of you that are wondering, and I haven't looked at the question list, although there are some out there, how much does this cost and when can I have it? I think the right answer is to tell you that the return on investment, the ROI, is less than 2 years, and that's not counting the decreased capital cost. It's simply evaluating the savings in electrical running costs, and that is it. And we'll get more to that. But the timing is we expect to start shipping this in Q2 of this coming year.
That's correct.
So this is a real technology that makes a big difference. Now, Mike, you told me something kind of stunning a little while ago. You told me that if a customer bought a transmitter sized for -20 today,
yes,
and were to add HD Power Boost in the future, that would take him all the way to -14.
correct.
So he doesn't have to go in and change his transmitter or change his antenna or anything. He just enables this feature, and he can take that transmitter sitting as no forklifts involved.
No forklifts. Very, very, very simple migration.
He can upgrade
path
all the way up to -14.
Right.
Pretty cool. Let's talk about where that efficiency comes from. These are the various injection levels that we've talked about, -10 all the way to -20. And we're looking at AC to RF efficiency. That is the AC power line coming into the transmitter as related to the RF power coming out the EIA flange at the output. And you can see the dollar savings for a year, assuming 10 cents per kilowatt hour.
That's correct.
In an NV40.
In a 24/7 station, yes.
That's right.
So at -10, we get the best bang for the buck.
That's right down here, $6,300.
Right.
U.S. or Canadian? U.S. I think.
It was 10 cents U.S. per
That's right.
kilowatt hour, so yeah.
Okay.
So with a larger peak to average signal, and -10,
Right.
Power Boost can work its magic
More effective.
more effectively. So
Sure.
the result is more savings.
But even if you're only using -20, $2,600 a year is not so bad.
That's correct.
Yep.
It's nothing to sneeze at.
Okay. And these are real numbers, and they assume 10 cents per kilowatt hour. I don't know anybody that thinks power costs are not going up.
That's right. I know.
Certainly
I
within the
pay
time frame.
12 at home.
Okay. Well, there you go.
Halifax, so.
Okay. Now, one thing I want to, let's change one thing. I want to take a look at a chart that we put together because a lot of people are trying to understand how they can apply this technology to their own TPO level.
Right.
And what this chart does is it allows you to plug your TPO level in here. Suppose you've got 17,000 watts of transmitter power output required. This tells you in the green, these are transmitters that support these various injection levels from -20 to -10 natively, where we don't have to add anything in addition to do that.
And the numbers that are shown in this table are the non-Power Boost
Right.
capabilities of that transmitter.
For those areas that are in blue, that means that the transmitter itself won't do it unless you add HD Power Boost.
Right.
And the area in yellow indicates transmitters that can be upgraded in place, where we can simply add some stuff to a transmitter. We're not, again, no forklift involved. We can add some stuff to upgrade the transmitter to be able to handle the increased power as necessary.
Correct.
So we think that this tool will help a lot of our customers understand what flexibility there is, what they should be looking at, and you've got an idea of what kind of injection level you're looking at. You can see how much you're covered. This tool will be available to our customers that contact our representatives directly by email or by phone, and within the next day or so we'll be sending this out. So this is a free tool that's available to everybody that will give you a much better understanding of what HD Power Boost and the in-cabinet upgrade can do for you. Any other comments here? Mike? Hal? No. Okay. So let's go back to the PowerPoint. And that. And we should be able to down here. So let's summarize a little bit what we've talked about. We're about 50 minutes into the webinar. HD injection level requirements range in general from -20 to -10 depending on the noise environment. And the good news is that a wide range of increased digital injection strategies exist. The Nautel has the only single box solid-state transmitter solution which will provide up to 44 kilowatts of analog power or 34 kilowatts at -14 dB. And as Mike said, you can buy for -20 today and get up to -14 dB with HD Power Boost later. Pretty cool. Now, we should mention that as our 40th anniversary is here, we have offered, and we've been offering the whole year, a 5-year warranty for new purchases of the NV series transmitter purchased within calendar year 2009. We also offer various financing options, including 12 months same as cash, and also customized packages up to 72 months subject to approval. And we also have the capability of taking trade-ins for you. So we're going to work with you to try to make sure that we can get you into a good Nautel transmitter properly, and these are the guys that can help you. This is St. Margaret's Bay right in front of our plant. This is the whole team from the Nautel sales department. You'll probably recognize your representative here along the left side, an overall email address, a sales email address. All these webinars are stored along with technical papers on our website, but you can contact these guys directly and they will help you with anything, any questions that you may have. Now, let's go to, we've exhausted the basic information that we wanted to communicate. Let's go to the questions and see if there's any questions here that we can answer here for people today. And let me see here, 1 second. If there's any questions that anyone has, you're welcome to post them on the web interface here. And let's see here. All right. And okay, this is a question. It says, okay, it says you mentioned a 10 dB combiner, 10% of which was of loss was analog, and 90% of the HD power goes to the reject load. Then you mentioned a 5 dB combiner, less HD power, but more analog power goes to the reject load. Please tell us exactly what percent of analog and HD goes to the reject load with a 5 dB combiner.
I don't have my calculator with me, but it's
Okay.
about 25%.
Okay, 25% of the
analog
analog
power gets thrown to the, and it's always the inverse.
So it's 75% of the digital.
Would be of the digital.
Okay, now this is important for two reasons, I think. One is the amount of actual power going to the load, the heat dissipation of that, all those sort of things. But another thing is that means you need about 25% headroom in your analog power transmitter.
Right, so the headroom that you have available may dictate the coupler ratio as opposed to the efficiency.
Right.
So you may be forced to take a non-optimal coupler value, which would result in less efficiency, more reject power.
Looking, we have a 7-year-old V7.5. What are the capabilities of our old transmitter? Our TPO is 4.3 kilowatts. I presume he's looking at hybrid mode at the moment.
Yes.
Right.
So 7.5 kilowatts would be approximately a V7.5 could do about 6 kilowatts in -20.
And that's not including HD Power Boost.
That's correct.
Okay. So he's got significant opportunities to upgrade that transmitter.
Yes.
Okay.
Without a doubt.
Okay. Let's see if there's any more questions here. I think we've hit them.
Should that not read higher or greater turnaround loss?
I think we can. I think we've answered that in the spoken part. Okay. I believe we've answered most of the questions. I'm not seeing additional ones popping up here. So with that, I want to thank everyone for your participation. If you're interested, we have a number of webinars coming up that you may find. We have one next Wednesday, a week from tomorrow, on the NX series transmitters, NX25, NX50, and we will be getting into the unique design features of that. You can see all the possible webinars we've got coming up, as well as register for them at www.nautel.com/webinars. So please please do register for those. We look forward to talking with you again, and thank you so much for attending Nautel webinar here in Halifax, Nova